In this lecture, we will study about the sequence impedance of transformers. So, what is the meaning of sequence impedance? Sequence impedance is that impedance which is offered to the current of a particular sequence or symmetrical component by the system. That is, if I say that it is positive sequence impedance, it means it is the impedance offered by the system to the flow of positive sequence currents. Similarly, the meaning of zero sequence impedance will be the impedance offered by the system to the flow of zero sequence currents. So in this way, these terms are defined. Now in this lecture, we will study about the sequence impedance of transformers. So as we know that there are, in the equivalent circuit model of a transformer, there are two kinds of impedances. First one is the series impedance and second is the shunt admittance. So let us say this is a transformer. So this is the equivalent circuit model of a transformer. These two parts, I have bifurcated the series impedance in two parts, and this is the shunt admittance. Now, you might have studied in your machines course that the series impedance is usually measured by the short circuit test and shunt admittance is usually measured by the open circuit test. Okay, so by short circuit test, what we actually get? We actually get R effective and the leakage reactance, and this open circuit test gives us the shunt admittance, which is nothing but the admittance which is giving path to the flow of magnetizing current. So this branch, this is representing the loss part, and this part is representing the path to the flow of magnetizing current. Okay, now we have already seen that in the power system, usually the R effective is neglected, especially for transformers above 500 kVA. This series impedance is approximately equal to the leakage reactance only. This is very negligible as compared to this part. Similarly, we already know that this can also be neglected in the study of power systems. Okay. However, we will try to describe the effect of various components whenever sequence currents are flowing into the transformer. Now, in a three-phase transformer, there can be three types of connection. First one is, I can make a three-phase transformer by connecting three numbers of single-phase transformers, or I can have a three-phase transformer by core type construction, and I can also have a shell type construction. Now I will try to draw the schematic of these three types of transformer. Okay, first we will consider a bank, a three-phase bank which is being made by three number of single-phase transformers. Okay, so here I will make this one. This is the first transformer, first single phase transformer. This is the second similar one phase transformer, and this is the third similar single phase transformer. Now let us put windings over them. So this is the primary winding for the first phase. This represents the primary winding for the second phase, and this represents the primary winding for the third phase. Let us say these primaries are connected in star and grounded. Okay, so this is one of the type of construction. I can make a three-phase bank using three single-phase transformers. The advantage of this kind of construction is that it can work in open delta also. If one of the windings fail, one transformer can be taken out for service. Similarly, I can make spare. I can keep spares in my inventory. It is having lesser size and lesser cost. Okay, to keep the spare one unit. However, the following two types of transformer are more economic and lesser in size when we make a three-phase transformer like this only, instead of using three single-phase transformers. Okay, so nowadays we usually have these kind of transformers. Okay, now let us try to discuss the positive sequence, negative sequence, and the zero sequence impedance for this kind of transformer construction. Okay, so let us say we connect a balanced positive sequence voltage source. Okay, now in this discussion we will discuss two parts. First will be the series impedance, and second one is the shunt admittance. Now first discuss the series impedance part. Let us say the positive sequence currents are flowing into the transformer. Okay, now you will find that the series impedance offered to the positive sequence current are exactly same as those offered to the negative sequence currents also. Since you see that this is a static device, so in determining the impedance, we never talked about the phase sequence. So for this transformer, a positive sequence current or a negative sequence current will see same kind of impedance, series impedance to its flow. So for this kind of transformer, positive sequence, negative sequence will be equal. Now let us see what happens when zero sequence currents are flowing into the transformer. Now you see that this transformer construction will give same path as that of the positive or negative sequence current. Same series path will be given. So the zero sequence current will see similar impedance to its flow. So these three sequence series impedance are equal for such kind of transformer. Now we will see what happens to the shunt admittance? The positive sequence shunt admittance, negative sequence shunt admittance, and the zero sequence shunt admittance in such kind of construction. That we will see in the next slide. Now let us see what happens to the shunt admittance. Now shunt admittance is nothing but the path impedance or admittance offered to the flow of exciting currents. So what are exciting currents? Those currents which are responsible for the creation of flux in the transformer core or the iron. Okay. So you see, if I flow positive sequence currents in this transformer, the exciting current, the path followed by the flux will be same as that of the negative sequence as well as the zero sequence. So for this kind of construction, that is three single phase transformer making a three phase transformer, the shunt admittance for the positive sequence, the negative sequence and the zero sequence will be equal. So for this kind of transformer, there is no difference in the impedances, various sequence impedance is offered, even for the series impedance as well as the shunt admittance. Now let us see what happens in a transformer which is having shell type construction. After that we will see core type construction. So in the next slide I will make a transformer which is having a shell type construction. Now in this slide I have drawn a shell type transformer as well as a core type transformer. Now first we will consider the case for series impedance offered by these transformer to various sequence currents. Now these both kind of transformer are static device and they do not differentiate according to the phase sequence. So the impedance offered to the flow of positive sequence current or the negative sequence current will be same. The leakage will be same, resistance will be same offered to the current. So we can safely say that the series impedance for positive sequence and negative sequence for both kind of transformer are equal. Okay. Now here I have shown the leakage path. Okay. Similarly, there can be leakage path in this transformer also. However, the path into the air is little lower in the shell type as compared to the core type. So theoretically, the zero sequence impedance or the reactance, leakage reactance offered by these kind of transformer will be little bit different than the positive and the negative sequence. Practically, the difference is very low and it is negligible. Okay. Now you see that the leakage flux, since a zero sequence current is unidirectional in nature, so the leakage will have to go through the air. Okay, this air path. Now this air path is having more reluctance, so the leakage flux will try to reduce. So because of this, the zero sequence impedance is little lower than these positive sequence and the negative sequence, that is this is lower. Okay. Similarly, this zero sequence impedance is little lower as compared to these two types of impedances. However, this difference is little bit more seen in a core type transformer as compared to a shell type transformer. For all practical reasons, these are taken as equal. That's why I have deleted that sign. Okay. Now let us study about the shunt admittance. Now as I already told that the shunt admittance is the admittance offered to the flow of excitation current. Okay. Now you see that the positive sequence flux or the negative sequence flux will be having same path in the iron as well as air. So the sequence admittance, this is the admittance offered, although we have neglected this part. Okay, so this shunt admittance offered to the flow of excitation current for the positive sequence and the negative sequence will be equal, because the flux will have same path in the iron, for the positive sequence and the negative sequence. In the shell type, the positive sequence flux will be having same path as that of negative sequence. Similarly, in a core type, the flux path for the positive and the negative sequence flux will be same. So the admittance, I will write Y to show admittance. This admittance is same for, let us say it is core type, and this is shell type. Okay, similarly I will write shell type, core type. Now this XM is usually very high, so this Y is negligible practically, or for all practical reasons, so it is usually neglected in the equivalent model studied in the power system. Now let us see what happens to the zero sequence excitation currents. Now, as I already told that the zero sequence currents are unidirectional in nature, so the flux created by them will be unidirectional. Okay. Now, in this diagram, the flux created by this winding will be in this direction only. Similarly, this will also create in this direction only. Similarly, this will also create flux in this direction only. Okay. However, since this is a shell type transformer, the flux will have a return path in the iron. Okay. These two limbs will provide a return path from the iron only. So this XM for the zero sequence excitation current, although will be quite similar to positive sequence and negative sequence, as well as we have seen in the single phase transformer, bank of 3 single phase transformer, the quantity will be same. However, there will be a little bit difference. If I draw those 3 banks, let me draw that again. The windings were placed like this. Now, if unidirectional current flow in these 3 windings, the flux will flow like this only, will have same path as the positive negative sequence and negative sequence. So again, y1 is equal to y2 is equal to 0, is equal to y0. Similarly, the case is same for this also. However, there is a little difference. What is that difference? You see that the iron path in a shell type transformer will be saturated very fast. When the quantity of flux will increase, the saturation will appear faster, because this is the same iron core. However, these iron cores are independent, so here saturation will occur at a higher voltage, but here in this case saturation will occur at a very lower voltage as compared to this kind of construction. So during saturation, this will vary very much. This quantity will have variation, a lot of variation. However, if we consider those variations also, practically this can be neglected for all 3 kind of admittances, positive, negative as well as zero sequence admittance, even if it varies with saturation. Now let us see what happens in a core type transformer. Now you see that the excitation current will flow and these will be unidirection. So the flux created by this winding will be in this direction. Similarly, this winding will also create in this direction. Similarly, this winding will also create in this direction. So all these currents will create flux in same direction. Now these fluxes are unidirectional, that is their sum will not be equal to 0 here. So these will have to return from somewhere. Where will they return from? They can only return from air. Okay, so the return path is from air only. So you see that the air will create reluctance in this. Because of this higher reluctance, Xm will reduce. When Xm will reduce, the zero sequence admittance will increase. So for that case, it is little higher as compared to these two. Okay, but still practically for all purposes these all can be neglected. So usually for a transformer, for any kind of construction, as a summary we can say, for the study of power system, the transformer can be represented by their positive, negative or zero sequence impedance, series impedance, and these are usually equal. Okay, for all practical purposes. Now based on the connection of the neutral or the various connection of the windings, the network, equivalent network for that kind of transformer, that we will see in a later lecture. Here I have just shown the impedance, not the connection of these impedance in a network. So in this way I think I have clearly told what is the difference in the positive sequence, the negative sequence and zero sequence series impedance, as well as shunt admittance for various kinds of construction of transformer. But practically I already told that this is the case for all practical purposes in a power system, since usually we are considering only those transformers which are having higher power ratings. Okay, so if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.